So if we're going to talk about bonding, we actually need to update our understanding of the octet rule that has been so well ingrained in us for years now. So where does that octet rule come from? Well, octet, again, came from 8 electrons, right? 8 electrons, which happen to be in the second row of the periodic table, where we were talking about the 2s orbital and our 2p orbital, right? And this had x, y, and z for our 2p orbitals. If each one of these orbitals can hold 2 electrons, right, this led us to a total of 8 electrons. And this was that idea of an octet. So if we're going to look at something like methane, right, and go back to our good old Lewis structure pictures for how we determined the octet rule for methane, what we said is that this carbon had these 4 bonds around it. Each of these bonds was signified by 2 electrons. And so we get to an octet. But if we take this a step back, right, where this came from was building from a Lewis structure, right? A carbon that has these 4 electrons and these hydrogens that each have their 1 electron, and we formed a bunch of these bonds. And so we use these Lewis pictures, right, to try to understand bonding. And it explained where this octet rule came from. But as we move to transition metal complexes, counting up the number of electrons is not so simple. Right here in our case of carbon, right, we can just pull this off of the periodic table. But when it comes to transition metals, we actually have different types of bonding that can occur. So we're going to take an example that's a little bit more complicated, actually a lot more complicated, and we're going to walk through how we can understand kind of the nuts and bolts of our transition metal complex. So what we're going to do is I'm going to draw a manganese complex here, and it's going to be octahedral. So if you're not comfortable with this, go back to that um, previous video where we talked about the different shapes of our organometallic complexes, right, or metallic complexes, I should say. Right, and if you want to think about this in 3 dimensions and kind of see how it looks if we rotate it around. You can try to build this in the program Avogadro, which is talked a little bit more about in the lab. It makes it easier to build these and look at these in 3 dimensions. And so now if we're looking at this complex, right, I can see here that this manganese has 6 different bonds. But I have to be careful with how I treat these bonds because they're not all the same. So what we are going to do is we're going to be doing what's called a covalent bond counting method. And what we're going to do is the same exact fundamental principle that we did with methane. What we're going to do when we look at this structure is we're going to break all of the bonds between the manganese and these different ligands, these things that are attached, and I'm going to evaluate them from there. So I'm going to have my manganese in the center, and we look on the periodic table and we can see that manganese has 7 valence electrons. So we'll come back to that in a second. All of these COs, right, these are carbon monoxide. It's a ligand. We're going to see a lot this quarter. Carbon monoxide is kind of interesting because if we draw out the formal charges, right, the carbon has a negative charge, but overall it is net neutral. And so we can see that if I'm going to kind of take a step back here, when I'm breaking these apart, I want to make neutral ligands. So sorry, I should have mentioned that earlier. So break bonds to get neutral ligands. Right, this is an important feature, and I kind of just skipped over what I was doing in this step. But we want to break our bonds to get neutral ligands. So carbon monoxide is neutral actually when it has this negative and positive charge. And I can see that there are a total of 4 carbon monoxides in this structure. I'm trying to draw them kind of in place with where they were in my first structure. All right. So again, if I want to make these neutral ligands, that means that my NH3, my amine, has 2 electrons and it is neutral. But now what do I do with the chlorine? All right, so my chlorine here, if it's going to be neutral, it has 7 valence electrons, right? It has 7 valence electrons to be neutral. And so what I can see here, if I go around and look at my ligands, right? When I broke this apart, I had 2 electrons from each of my carbon monoxides. I have 2 electrons that were involved in the bond with my ammonia, right, the amine. And I only had 1 electron that came from the chlorine. And so this is where we're going to get some new names. So L-type ligands are 2 electron neutral donors. Meaning when I put this together, right, the ammonia, all my carbon monoxides, each of those had 2 electrons that they used to form that bond with the manganese. We're going to call something an X-type ligand if it's a 1 electron donor, right? So in this case, chlorine is a X-type ligand. It is a 1 electron donor. And so what do we do with all this? So what we're going to do is we're going to take this structure and we're going to reevaluate it. And we're going to do some counting up of our electrons, very much like we did with methane. Okay. So we're going to do pretty much the same thing that we did with methane. And so we're going to say I have my CO ligands, right? And I have 5 of them, and each one was a 2 electron donor. That means that if I'm looking at my manganese, right, surrounding that had 10 electrons just from carbon monoxide. Similarly, my ammonia, I had 1 of these, and it was a 2 electron donor. So that means that I had 2 electrons coming from my ammonia. The Cl, I had 1 of these, and I said that this was a special 1 electron donor. So I have my 1 electron here. And then my manganese, right, my manganese here, I'd have to look at the periodic table to see how many valence electrons manganese has. Oh, sorry, I need to go back and fix something. There were not 5 COs, there were 4 COs. Because again, algebra and math are hard sometimes. We're going to work our way through it. So sorry about that if you go back and fix this. So we have 4 of these carbon monoxide ligands. Each one's a 2 electron donor. So that means that we have 8 electrons total. And if we look at manganese on the periodic table, can see that manganese has 7 valence electrons, right? So that means that manganese brought 7 electrons to this party. Now, why we need to include this is because those 7 electrons aren't actually represented on the Lewis structure, right? If we go back to how we draw ammonia or carbon monoxide, we always draw all of our Lewis or our valence electrons. But we can't do that for these transition metals because we just have so freaking many electrons to deal with. So now if we're going to add these up, we see that this has a total of 18 electrons around my metal center. And so, well, how do we get to 18, right? Or what does this mean? If we go back to octet, meaning 8, and that was our s and p orbitals. If we have an s orbital, we have 3 different p orbitals, and we have 5 different d orbitals. That means that we have a total of 9 orbitals in a given quantum level, which means we can hold 18 electrons. Now, when it comes to inorganic chemistry, this is not a rule like the octet rule. There are many, many violations to this, but generally 18 electron complexes can be very stable. And again, this just is a parallel to our octet rule that we use for organic chemistry. Okay, so we can do electron counting, right? And so we can figure out this total electron count. So let's look at what we've done so far. We've classified things as X or L-type ligands. You might see these referred to as anionic or neutral ligands. We'll get to that in a second. So now what we need to do is and we've also figured out the total electron count, right? So we were able to count up the total number of electrons. So let's look at our other learning goals that we have for right now. We need to determine the oxidation state of our metal. And so right here, I'm talking about this as if it's manganese 0 straight off the periodic table. But we know that the oxidation state's different. So we're going to use a simplified method here because oxidation states are really just a bookkeeping measure, right? So we just have to have a way of approximating this. So the oxidation state of a metal, we're going to say is just equal to the overall charge, right? And so in this case, the overall charge is 0. It is neutral, right? There's no charge on this complex. So the overall charge plus our number of X-type ligands. Right? So for this particular manganese example, this would be 0 plus 1 because our chloride is our only X-type ligand. So the oxidation state of manganese, in this case, is formally plus 1. Right? This is our oxidation state of the metal, and this can be important for determining reactivity, and this is something we're going to be kind of using throughout the quarter. So now we have we can figure out the total electron count for our system, and we can determine the oxidation state of the transition metal, and that just being the overall charge and the number of X-type ligands. So if we're looking at this as kind of a checklist here, the last thing that we need to figure out how to do, right, is calculate our d electron count. So what on earth do I mean by this d electron count? So let's look here at manganese, right? We said that it was plus 1 as its formal oxidation state. And so again, we go to that periodic table and we saw that manganese had 7 valence electrons when it was neutral. Right? 7 valence electrons when it was neutral. However, this oxidation state of plus 1 means that it lost, right, 1 electron. So that means that manganese, in this case, right, after we've assigned its oxidation state, actually has 6 valence electrons. And for reasons that we will talk about later, all of the valence electrons for a transition metal end up in d orbitals when in a complex, right? So when complexed, meaning bonds, right? When it has bonds to the transition metal, all the valence electrons go into d orbitals. And what this means is that when we have a manganese that is plus 1, we would refer to this as a D6 metal. Right? We're going to talk about d electron counts a lot in this course. It's actually going to be probably more useful to be able to count up d electrons than it will to count up the total number of electrons for a complex. Right? So this is how we can calculate the d electrons. It's just the oxidation state of the metal, or I should say the valence electrons of the metal minus the oxidation state. Right? So the d electrons equals valence electrons minus the oxidation state. All right, and we're going to get some practice with this in class. We're actually going to get a lot of practice with this in class on Wednesday and Friday. So now that you've made it through this video, there's a PDF that's posted, right? So I'm going to say, read the PDF. That's called a primer on the 18 electron rule or the 18 electron complexes. And that's going to give a text kind of version of this. It's also going to introduce a different method, right? So there's 2 methods. What I did here was the covalent method, right? The PDF also introduces the ionic method. And in class on Wednesday, I'll compare and contrast these just real quick to talk about the differences. They end up with the same exact conclusions. So whether you use the covalent or the ionic method, you'll end up with the same oxidation state, the same d electron count, and the same count for total electrons. It's just a way of approaching it that's slightly different. So they kind of have each have their pros and cons. I'm actually a recent convert towards the covalent method over the ionic method. So go ahead and read this PDF. You'll be ready to come to class on Wednesday, where we're going to do some more practice with electron spin states, which are going to be foundational for inorganic chemistry, as well as practice on electron